Good day to you. All living things live in fluid environments, and a significant part of the adaptation of organisms to environments is in understanding how organisms interact with these fluid environments. Now, a key tool in helping us to understand this is the Reynolds number, which we've introduced in other physics of life episodes. This quantity, which is the ratio of the inertial and viscous forces acting on an object in a flowing fluid, provides a foundation for analyzing the flow of any fluid around any object of any size. But more useful, perhaps, is that careful use of the Reynolds number enables us to quickly and very efficiently get to interesting questions that we might ask about adaptation in fluid environments. And today we're going to look at one example of how this can be done. Before we get to the physics, let's start with the interesting biological question. This is a collection of succulent plants, and of course succulent plants are found throughout the tropical and subtropical deserts of the world. And these plants, as you can see here, come in a variety of shapes, interesting shapes. For example, if we look over here at this cactus, this is a very smooth shape. It's almost like a little ball. You can see the ball shape if we look over at this cactus right over here. It's somewhat spherical, as well as this cactus right over here. But other of these succulent plants, like this large cactus, or over here, they're tall and they're tall and cylindrical. And in some instances, for example, if we look at this cactus right over here, or this one, there's some interesting fluting patterns along the surface of this plant. Some coming back to this one over here, they are relatively smooth. And so there's quite a bit of interesting variation in the shape of these succulent plants. Now, these plants are succulent because, of course, they live in dry environments, and that means they have to store quite a bit of water. This is what makes them succulent plants. And this store of water tends to make succulent plants a tempting target for animals that might want to come along, thirsty animals that might want to come along and actually steal the water that these plants have done such hard work storing up. So as a consequence, one of the adaptations that many succulent plants have is to defend themselves against attack by herbivores. And this is one reason why, for example, in a plant like this, you see all these large stabbing spines over here. If a thirsty herbivore comes up and tries to drink from it, it'll get a stab from one of these, and they do hurt, and that will tend to deter the herbivore from wanting to eat it. But that can't be the whole story, because the other interesting aspect of succulent plants is variation in the shape and the morphology of these spines. So for example, in some instances, like this very spiny cactus over here, you have very obvious and very sharp needle-like spines that can stab whatever herbivore comes along and wants to try to eat it. But on the other hand, you have plants like this plant over here, this large fluted plant, in which the spines are very, very small. It wouldn't act like much of a deterrence there. To this plant right over here, and you can see that there are almost no spines on the surface of that plant. And in addition, the spines can be modified in various ways. These are just plant hairs that are consolidated into a single stabbing needle. But in many cases, these plant spines differentiate into tufts of cottony fibers. For example, if we look over on this spherical plant right here, we can see that the spines are somewhat hair-like. On this one with the very pretty flower right here, you can see tufts of nice cottony wool coming onto the surface of that. In some instances, the cottony wool actually envelops the plant completely, such as in this one right over here, or in this one right over here. And in some instances, the spines actually weave the plant and swaddle it into a kind of a nice, interesting basket shape over here. And of course, in some instances, like this plant right here, as we said, the spines are almost absent altogether. So there must be something else going on with these spines other than deterrence of herbivores that want to come along and eat these plants and take their water. So what else is going on here? Well, what might be going on is that the spines and shapes of these plants might be affecting how they interact with wind. These plants live in quite harsh physical environments, and interaction with wind is probably an important part of their ecology and in helping them cope to the kinds of harsh environments that they live in. Deserts are quite frequently hot, for example, and plants living there can use wind to help shed the excess heat that they might absorb from the sun. But of course, deserts can also be quite cold, paradoxically, and there may be circumstances where a plant might want to actually conserve heat within it. And of course, deserts, being deserts, are also very, very dry, and it turns out that interaction with wind can also affect the rate at which a plant will lose water vapor to the air. So here's the interesting question. Could these variations of spine shape and these variations of plant shape play any role in how plants interact with wind and how it might help shape the way that plants lose heat to the atmosphere? Now, in order to answer this question, we first have to know something about how air actually flows around a plant. And this would be an easy question to answer if we could somehow visualize the flow. But visualizing flow is actually quite difficult in air. Things go very fast, and it's hard to mark air with a nice dye that stands out prominently like fluorescein does in water. But we might be able to visualize flow better if we could take these plants and put them in water and see how that fluid flows around them. But of course, we have to ask the question, what would looking at flow in water tell us about how air flows around these plants in air? Well, the good news is that the answer is that it's going to tell us everything that we need to know, but we need to be a little bit careful about it. We need to play our cards right. And the ace up our sleeve in this instance is the Reynolds number. Let's look at the Reynolds number in more detail. Here on the computer screen, right here, here's the formula for the Reynolds number. The Reynolds number is RE, and it's the ratio of the inertial forces of the fluid over the viscous forces of the fluid that tend to impede flow. We can make this a bit more detailed. The Reynolds number is equal to the ratio of rho, the density, times the length of an object. In this case, it will be the diameter of the cactus, times the velocity of flow past the plant, divided by the viscosity symbolized by mu. Now suppose we had a plant, and I'm just going to measure one over here. I'm going to put up a ruler next to this plant right here, and the diameter of this plant is about 7 centimeters or so. All right, so that's the dimension, the length term that we're going to be putting into our calculation. So let's just calculate what that would be. That's 7 centimeters is 0.07 meters. And let's say that we want to find out what happens to flow at a wind speed of about 5 meters per second. So let's just put 5 meters per second in there. Now, in air, with this viscosity and this density, that's going to give us a Reynolds number of about 23,000 or so. And if we look at flows in water, if we have a Reynolds number in water of the same magnitude, then we can be assured that the flows in water are going to be very similar to the kinds of flows that we see in air. But of course, we can't quite do that yet, because let's work out our calculations over here. We're dealing with the actual cactus itself, and so we're going to put in a number, 0.07 centimeters, because it's going to be the same size. And it turns out that a plant sitting in air at a wind speed of 5 meters per second is going to have a Reynolds number of 23,000. In water, you'll have the same Reynolds number of 23,000 at a velocity of flow of about 0.33 meters per second. So if we immerse this plant in water and mark the flows with dye, we can actually follow the flows in some detail. There's an additional bonus, and that is if we look at the velocity of flow, it's about 15 times slower in water than it would be in air to give us the same Reynolds number. Now, when it comes down to filming it, it's much easier to film things. It's kind of a natural slow motion that lets us follow the flows in some detail. So, as long as we can take a plant, immerse it in water at a velocity of about 0.33 meters per second, we can visualize the flows, and we can be reasonably confident that it's going to be similar to the flows that a plant would experience in air at a wind speed of about 5 meters per second. So, there's what we need to do to be able to do the experiment. And all we need to do now is do the experiment. So, let's go over to the hydrology lab and sink a few plants and watch how water flows around them. For our experiment, we took advantage of ESF's Arid Zone plant collection, curated by Terry Ettinger. The collection hosts a variety of succulent plants drawn from arid zones all over the world. The diversity of these succulents is truly remarkable. We're going to draw on 5 columnar succulents that vary in shape of the column and in density and shape of the spines. Once we selected them, we took them over to the large flume housed in ESF's Hydrology and Hydraulics Laboratory to study the flow. The first plant we will use is from the succulent karoo of northwestern South Africa. This is the baseball euphorbia, Euphorbia obesa, known in Afrikaans as the vetmensie, or little fat man. It is found along high ridges of this mountainous area and grows well in open sun. It can often be quite cold in these areas. The vetmensie represents one extreme of the plant shapes we will study. Like many of the euphorbias, the stalk is fluted, but the fluting is very shallow, giving the plant a rounded cross-section. The spines are also quite small, which presents a relatively smooth surface to the wind. As we can see, flow around the vetmensie is fairly smooth. Although there is a considerable turbulent wake generated behind the plant, flow over the plant is smooth and almost laminar. Note in particular how quickly the dye dissipates once the dye injection is cut off here. This means there's a rapid turnover of air close to the surface of the plant. Our next plant will be a species of cereus, a genus of night-blooming cacti that are found in the deserts of the American Southwest. This group is commonly found in flat desert washes and is often found in the shade of another plant. This species has the deeply fluted cross-section that is typical of the genus. In this species, the spines are still quite small. The pattern of flow is a little different from what we saw in the smoother vetmensie. Now, retained vortices are generated in the deep flutes. Note also how the vortices spread vertically within the flute. This indicates that there is a vigorous vertical mixing of air within the flute. This will facilitate the transfer of heat from the plant to the air. This facilitation of convection heat loss is one of the ways desert plants keep cool. Notice also how dye dissipates rapidly once the dye injection is cut off here. Let's have another look at that. Vigorous generation of vortices, extensive vertical mixing within the flute, and rapid dissipation of the air within the flute. The next plant is another species of cereus and is also found in the Chihuahuan and Sonoran deserts, but usually in sunnier conditions. This species differs from the smooth cereus in some significant ways. The fluting is still fairly deep, but now the ridges have tufts of large and robust spines lined up along them. These obviously deter herbivores, but they also impact upon airflow around the cactus. Air within the flutes is still vigorously mixed, but now the extent of the vertical mixing is greater than it was with the spineless cereus. The spines are apparently impeding downward flow enough so that fluid is retained in the flutes for a little longer. In slow motion, we can see the circular motion of the vortices within the flute. Dye still clears quite rapidly from the flute once dye injection is cut off. Again, this indicates that the fluting and spines enhance convection heat transfer from the cactus to the air. This is in keeping with this plant's tendency to inhabit sunnier environments than our spineless cereus. We now turn to our fourth plant. This is the columnar cactus, Espostoa, or old man cactus, found in the equatorial Andean highlands. It is usually found in the open, exposed to strong winds, cold temperature, and full sunlight. Like many columnar cacti, the surface of the plant is vertically fluted. What is most interesting about this species is its spines, which emerge as tufts of cottony fibers that merge and envelop the plant. The flow around this plant is also unlike what we have seen so far. For example, the fluting of the cereus cacti we have just seen generates considerable turbulence, so that the wake behind the plant is very perturbed. The wake behind Espostoa, on the other hand, is almost laminar in organization. There is turbulence, to be sure, but it is not nearly as intense as in the spiny cacti. The other notable thing is the turnover time of fluid near the surface. In the spiny cacti, dye cleared away from the plant quickly once dye injection was cut off. In Espostoa, however, the dye takes a longer time to clear.
Here, fluid is being retained at the surface for a longer time. In short, convection transfer from Espostoa is not being enhanced by its spines, but impeded. Finally, we turn to our last plant, Eriocerius, or mountain cereus, also known as the Old Man of the Andes. Like Espostoa, Eriocerius is a mountain succulent, but its distribution is mostly subtropical, located in the Andean highlands of southern Peru and northern Argentina. Subtropical climates often experience quite extreme temperature variations. Eriocerius is also a hirsute cactus, the cottony growth from its spines swaddling the plant in a furry layer. Flow around Eriocerius is much like what we saw in Espostoa. The hirsute layer seems to tame the wake behind the plant so that it is considerably less perturbed than it is for the spiny cacti. Also like Espostoa, the clearance of dye from around the plant is also quite slow. Indeed, compared to Espostoa, fluid turnover near the surface of Eriocerius is even slower. Thus the spines of Eriocerius impede convection transfer even more.
Okay, we're back. That was fun. Thanks to the hydrology people for helping us with this. So let's take a few moments to review what we've learned about how water flows around these plants. First of all, we saw that plant shape has some pretty interesting effects on the way that water flows around the plant. If the plant surface is smooth, as is the case in our euphorbia right here, then the flows were pretty laminar over most of the plant surface. When you come over to a plant like this cereus with the deep flutes in here, we saw that the effect of the flutes is to increase turbulent flow around the plant. And specifically, we saw that there's a great deal of vertical mixing within these flutes that takes place as a result of that turbulence. And the effect of the spines in this case, as in the case of this spiny cereus over here, in the case of the spines, what those did was actually slow down the flow enough, and what that did was it actually increased the vertical mixing of air within those flutes. We saw something very different in the plants that are enveloped in the cottony spines, such as this fellow right over here and this fellow right over here. What we saw there was that in both cases, the effect of those modified spines is to laminarize flow over the surface and to slow down the turnover of air around there. Okay, so now let's have a look at what that means for adaptation of the plants to desert conditions. Let's take a very simple scenario first. Let's take a plant that is sitting in an environment, sitting on the ground, and that plant is exposed to sun. That sun is going to be putting out solar radiation, and there's going to be some flow of heat into that plant that we'll call Q. That's the solar radiation coming in. What wind is going to do is it's going to actually carry this flow away, this heat away, and it's going to carry with it a certain loss of heat that we'll call Q sub convection. And the temperature that the plant will come to is going to depend upon the balance of these two flows of heat. When it's sitting in an environment, the sun is the sun, and it's going to be putting in a certain amount of heat, but what's going to really affect the temperature is what happens with the loss of heat by convection. Now, if you have a high rate of heat loss by convection, what that's going to do is it's going to ensure that the plant will come to a temperature equilibrium at a low temperature, relatively low temperature. And there are a couple of ways in which this can happen. Suppose you have an air temperature that is quite cool. That's going to carry away heat at a certain rate, and the colder the air temperature, the greater the heat loss will be. And as a consequence, what you're going to end up doing is that the plant will come to thermal equilibrium at a low temperature. On the other hand, you can also manipulate this by manipulating the flows over the plant surface. And depending upon what the flow is, that's going to affect how much heat can be carried away by convection. And what that's going to do is that's going to provide an independent means of adaptation to temperature, hot temperature or cold temperature in desert environments. Now, in general, if you have a laminar flow over the surface of an object, what that's going to do is it's going to act as a relative impedance to heat loss from the plant. On the other hand, if you have a turbulent flow over it, that's going to tend to promote heat loss. So when you have a plant that is experiencing laminar flow across it, that's going to come to a temperature equilibrium higher than if you have a plant with turbulent flow flowing past it. And that's how we can interpret the results that we had over here with our plants. In the case of the smooth the smooth euphorbia right here, we saw that in this instance that the flows were fairly laminar. Even though flow went fairly quickly past it, nevertheless the flows were laminar compared to the fluted plants like this smooth cereus, or over here this spiny cereus. In the case of our euphorbia, these plants live in fairly high desert environments. It can be quite cold there. And in that instance, if you have laminar flow over there, that plant is going to come to a higher equilibrium temperature than it would if you had nice turbulent flow. On the other hand, these two fluted cereus over here, they live in hotter environments. This one lives in shade. This one lives in open sun. And this one generates turbulence at a greater rate than does this one. And therefore, this one is going to be able to dissipate solar heat, the extrasolar heat, better than this one will. But they both live in fairly hot environments, and so the presence of the fluting helps to promote heat loss generally from these plants because they are such effective turbulence generators. The fluting is one aspect of the generation of turbulence. The many small barriers to flow that are presented by these spines are another generator of turbulence. And so if we look at these three plants, our euphorbia, our smooth cereus, and our spiny cereus over here, we see a rough gradation in increasing turbulence that is generated by flow going around it. This plant, which lives in relatively cool, sunny environments, is going to want to not lose a lot of heat by convection. That is, it's going to want to hold its heat in. Therefore, you don't have a lot of turbulence generating devices there. This plant, the spiny cereus, lives in full sun, and it's going to have a lot of heat to be able to dissipate. And it does so by having not only fluting, but it also has these many turbulence generating spines. And then finally, our smooth cereus here lives in hot air, but it lives in fairly shady environments, and so the need to dissipate heat is somewhat less here. Still, the need to dissipate heat in this plant is greater than is the need in our smooth euphorbia over here, and this has these turbulence generating flutes that run along the surface of the plant. Okay, well, what about our other two plants? We did experiments on two other plants, this one right here and this one right over here, both of which have their spines modified into quite dense mats of cottony fibers that envelop the plant. Now, what's interesting about these two plants is that these two plants are both inhabitants of high desert environments. In some instances, they inhabit quite cold environments. And in that instance, those plants may want to have every joule of energy that they can get from the sun. In other words, because these plants live in fairly cold air temperatures, they may want to actually impede heat loss to the environment, and the way they do that is to envelop the plant in these nice swaddles of cottony fibers. And as we saw in the video, not only does this relaminarize the flow, which impedes heat loss by convection, but it also tends to retain air near the surface of the plant underneath the mat, and both of those will result in a smaller rate of convection heat loss to the environment compared to these two plants right over here. So in this instance, in the case of our two furry succulents, these have actually modified their spines to act as dampers of turbulence and impeders of heat loss. And so that's the outcome of our experiment. And with a little intelligent use of the Reynolds number, what we've managed to do, actually with a minimum of effort, is to identify two possible adaptations of plants, desert plants, to the harsh conditions that they are likely to encounter. One of them involves this variation of plant shape, ranging from spherical to fluted to very strongly generated, very strongly festooned with spines. And the other, of course, involves adaptations involving the spines, from having none at all, to having small spines, to quite spiky spines, to having these spines modified into these insulating coats that surround the plant. Now, so far, what we've done with the Reynolds number and with our flow experiments is that we have actually generated sharp hypotheses that we can go out in the real world now and now test with other kinds of measurements. But of course, in order to be a scientist, you have to have those sharp hypotheses to begin with. And the use of the Reynolds number that enabled us to actually look at flows in some detail fairly simply and fairly quickly was a very important part of helping us get to those sharp hypotheses quickly and efficiently in ways that we can actually go out and study the adaptations of plants in the real world. Okay, well, that's all for now, and we will see you another time.